Hi, some of you are concerned with problem with fluids, and I just wanted to go over this problem. It's a pretty standard one. What if you have a tank of fluid like this, and somewhere in the bottom, or near the bottom, you have a little nozzle that's sticking out, and water is just flowing out of that little nozzle like this. You've all seen this kind of thing. If you have a soda can filled with something, you poke a little hole in the bottom, then certainly the water is going to flow out. So what's the velocity there at the point where it comes out? How can we figure this out? Well, the way to solve this is using Bernoulli's equation, as I'll explain in the next frame. And what you want to do is basically compare 2 points. So let's take a look at this. So let's look up here at point 1. So imagine a point at the surface of the fluid up there. We'll call that point 1. And imagine another point down here, point 2, which is right at the point where the nozzle opens up into the outside atmosphere. And Bernoulli's equation, you might remember, is basically a statement of the energy of everything at point 1 and comparing that to the energy of everything at point 2. If we assume in P2O1 land that there is no friction, then energy is going to be conserved. And the energy has different forms. This is potential energy due to gravity, rho times g times h. This is kinetic energy, 1/2 rho v squared. And then this is energy that's due to basically the pressure of all the molecules pushing against each other. And at a microscopic level, it's related to the kinetic energy of the different particles that are moving around. But for our purposes, just worry about these 3 things, right? Gravitational potential energy, kinetic energy, and then pressure energy. So here, for point 1, it's elevated at height h above. So point 1 here is above point 2 by a distance of h. So I've got that height there. Whereas for point 2, we'll call this ground level right there, or the point that we're going to compare it to. So we'll say it has a height of 0. Okay? So that's the gravitational potential energy of point 1. It's greater than the gravitational potential energy at point 2. The velocity here at point 1 is going to be close to 0, as we'll find out in a minute, but we just want to write that term down there. So it's a lot like the kinetic energy term 1/2 mv squared, except with fluids we're dealing with density, not with masses. And then up here for P1, the pressure is just the atmospheric pressure. So for point 2, it's definitely coming out at a particular velocity. So that's some velocity down at the nozzle. And then there will also be a pressure here right at the point where the nozzle is exposed to the external atmosphere. And in fact, the pressure there must be the same as the atmospheric pressure because it's exposed to the air. So this pressure is atmospheric pressure, and this pressure is atmospheric pressure. So we'll use those facts to simplify these equations, as I'll show in the next frame here. And what we have is, as I said, there's atmospheric pressure of P1 up at the top. There's also atmospheric pressure of P2 at the nozzle where it comes out. These guys will cancel, okay? And here we have the gravitational potential energy, rho gh. Here, the gravitational potential energy is 0 because, there's no height to that guy. If we're measuring the height of P1 with respect to P2, we'll call P1 at height h, and then we'll call this guy at 0. Okay, so that term goes to 0. The velocity at P1 is 0, so this term drops out. So 1/2 rho v1 squared, it's not really moving, it's just sitting there stationary. You can imagine putting a little feather on the top of the fluid and it's barely moving at all. So velocity is approximately 0. All right, so here we have all potential energy. This is point 1. And then down here at the nozzle, we pretty much have all kinetic energy. Everything's coming out. And the atmospheric pressures, as I said, they will cancel like that. So we say rho gh equals 1/2 rho v2 squared. We find out that the rho's cancel, and then we multiply both sides by 2. We get 2gh equals v2 squared. And then I can take the square root of that, and I get the square root of 2gh equals the velocity coming out at the nozzle. So if in a problem, let's say on the final exam, they give you numbers, you could plug those guys in and you could solve that problem according to this explanation. So hopefully you understood the principles behind it. Roughly speaking, again, what you want to do is use Bernoulli's equation. It's conservation of energy. You compare a point at the top to a point right here at the nozzle where it's coming out. Hopefully that was helpful to you, and please leave comments below if you have any questions.